I think we can start. So in the last lecture, which was last Saturday, we started talking about, or we actually discussed one type of sampling algorithm, which was the rejection sampling. And in rejection sampling, the idea was that you will have a proposal distribution, QX. From the proposal, you will draw sample, and then you will reject it or accept it based on certain criteria. And the hope is that whatever you are accepting, those samples will now come from or will belong to the target distribution. So very briefly, what you see on bottom left is the rejection sampling algorithm. Bottom left. So what you do is you sample from some proposal, which is Q. As I said that throughout this sampling distribution or sampling based algorithm part, we will be denoting Q as our proposal distribution. So you sample from Q, and then you accept that or reject that based on certain criteria, which is there in the accept, the second line. Okay, and if the criteria is not satisfied, you reject it. As simple as that. Okay. And this is all well and good, but there is one problem here. What is the problem? Can someone remind me what is the problem with rejection sampling? No, with rejection sampling. What is the problem with rejection sampling? The fact that you reject samples, that itself is the problem, because what if your acceptance ratio is 1%? What does it mean? It means that if you need one sample, you have to actually draw 100 samples. If you need 10 samples, you have to draw 1000 samples, so that 100 ratio will go on. So if you need 1 lakh sample, you have to 1 crore sample is what you will actually have to sample, and then only 1 lakh will probably get accepted. If that is the case, like 1%, I'm saying 1% of the sample will get accepted. Okay, so that is a tricky situation. So the point is that, and that can very easily happen if your proposal is not a good proposal. We have discussed that what is a valid proposal, but we never discuss what is a good proposal. And we cannot discuss what is a good proposal because there is no such criteria mathematically. Yes, theoretically we know a good proposal is a proposal which is as close as possible to the target distribution. A good proposal, the best proposal is the target distribution, but then you can't sample from it. So what will I do with that good proposal? Okay, so we always work with not so good proposals. We always have samples getting rejected in bulk, and we always will end up with acceptance ratio which is probably 10% or 5%, even for simpler problem. And if it is a really high dimensional problem, that percentage can mean fraction. So long story short, the problem of rejection sampling is that samples are getting rejected. That is the problem. Okay, and that actually motivates what we are going to discuss today. So the question we should be asking is that what is the ideal acceptance ratio? When should we be really happy? What do you think is the ideal acceptance ratio? 100%? Everything should be accepted, as simple as that, right? So in other words, can we devise a sampling scheme where all samples will be used, no samples will be rejected? Obviously, you can think that, okay, I am going to sample from the target itself. That I cannot do. So we want to devise a sampling algorithm where we will not be sampling from the target. We cannot sample from the target. We will be sampling from some proposal, but all our samples will be accepted, because that is the optimal scenario we can have. And one algorithm that does that is the importance sampling. Okay, so in rejection sampling, we reject many samples. Okay, and the number of samples getting rejected increases as you go to higher dimension. Okay, so ideally we will like to use all the samples. Okay, we will want to use all the samples. Why would I even want to reject samples? Given that all those samples represent my distribution, it's not that I will just arbitrarily accept everything. Every sample should be used and will be used to represent the target distribution. So this basically means that can we have an algorithm where no samples are rejected. Okay, can we have an algorithm where no samples are rejected, which means every sample is used? Importance sampling is one such algorithm. Importance sampling is the answer to this, is the answer. Okay, importance sampling is the answer to this question. No, we want to use all samples. If we have to use all samples, nothing can be rejected. So 0% rejection. We'll see that. Let's see. Okay, so importance sampling is the answer. So naturally, the question comes, as the question was asked rightly, that is that even possible that all samples will be used? So let us see, and let us start talking about the algorithm, the importance sampling algorithm. And from there, from the importance sampling algorithm, we'll try to understand what we are trying to do. Okay. So before we talk about importance sampling algorithm or the algorithm itself, let us talk about two things. Things that we have discussed earlier, but let us bring that back because those will be needed to discuss importance sampling. Okay. So the first thing that we have discussed earlier is that, so why are we sampling? Can someone remind me? Why are we sampling? What is the purpose of sampling? To approximate a distribution, but why do we want to approximate a distribution? Because, but why do we want to know it? Think of a posterior, right? Why do we want to calculate the posterior? To make prediction. And how do you make prediction? By computing the predictive distribution. And what is the predictive distribution? An integration. So at the end of the day, what are we trying to do? Integration. So we are trying to draw samples to represent integration in a summation form. That's the law of large number. That expectation is an integration, and we want to compute expectation, and we want to write expectation in terms of the samples, because we cannot solve that high dimensional integral. Even the evidence that I earlier said that is intractable, it is intractable, that is an integral. If I have to compute the evidence, I have to solve a high dimensional integral, right? So the point is that if you think carefully, throughout this course we are only solving integration. And when I say integration, we are only using the sum law. We use the sum and product law. What is sum law? Integration in the continuous form, right? So essentially we want to solve integration. So we will devise this algorithm as a tool for solving integral. Okay. So essentially essentially we want to solve integrals and compute expectation. Okay. No matter what calculation you think of, you will realize there is some expectation calculation that is there in your maths. Like the predictive distribution, that is nothing but expectation of the likelihood with respect to the posterior distribution, because it is integration of the likelihood times posterior d of theta, right? So what is that? That is expectation, right? So just for example, we want to predict, right? We want to predict, and for that we calculate probability of y star given x star comma x comma y, and we have seen that this is equal to integration probability of y star given x star comma theta multiplied by probability of theta given data, which is x comma y d theta, right? What is this? This is expectation with respect to the posterior. This is nothing but expectation of probability of y star given x star comma theta, and you are drawing sample from probability of theta given d, isn't it? So whatever calculation we are doing, if you think carefully, have a closer look, either that is an expectation or that involves some expectation. Okay, and generally the bottleneck is where expectation is needed. Case in point, the evidence, that's the expectation. Okay, clear? Okay, the second point I want to try to make here is that once or from law of large number LLN, we know that if you have to compute what expectation of fx with respect to pi, this is approximately equal to, you will draw sample from pi and then 1 by n summation over I f of xi. We have seen that, we have seen this expression, right? Expectation is nothing but you will draw samples from the distribution, in this case that is pi, and then use those samples to represent the expectation. Nothing new. Not only that, we have also seen an important thing, that is the empirical distribution. So pi of x you can represent using the samples as 1 by n summation over I delta xi x. This is our empirical distribution, if you remember, where delta is our direct delta function, right? So at each point it's a direct delta function and it's a mean of that. So now if you look into this representation, the empirical distribution, okay, can we think or can we say that here we have n number of samples and each sample is weighted 1 by n? Is it not? We have n samples and weight of each sample is equally weighted, which is 1 by n, correct? So if 1 by n is the weight and that is the equal weight, can't we have a scenario where we have samples, but the samples are having their own weights? Some sample is having higher weight, some sample is having lesser weight. That is possible. That is the concept that we will use in importance sampling. We will draw samples from proposal, but we will use all the samples, but some sample will have higher weight, some sample will have lower weight. So here 1 by n is the weight, and all samples have equal weight. Okay, and that weight is 1 by n, because it is xi by 1 by n, I mean 1 by n delta xi, 1 by n you can put inside, right. So, in importance sampling, we will assign different weights to different samples. Okay, how will that happen? How will I do that? How will that satisfy things? Will that be a good estimator and all those things? We'll see that. But just to give you the high level picture, what is coming maybe in the next slide is that we will assign different weights to different particles, or in some sense we'll do that. Okay. Okay. So with this background, we have established two things or stated two things. One is that mostly or almost always we are interested in computing integration, expectation to be more specific, right. And second, it is not necessary that each sample will be equally weighted. Samples can have different weights, right. Now these two things will come together in importance sampling, and let us see how. So suppose we are interested in computing expectation with respect to the distribution pi of fx. By the way, this pi I am writing at the suffix or subscript is a new notation that I am introducing today. Previously I was not writing that because I was always assuming it is coming from one distribution. But now you will see that I will assume that sample is coming from two distributions. So that's why, to denote from which distribution I am sampling, that I am writing in the subscript. So whatever is in the subscript, that is the distribution from which you will sample or I will sample. So that is a notation, very standard notation in Bishop, in Murphy, in all those books, you will find that notation. That's a very standard notation. Okay. So I am interested in computing this thing. So mathematically, in the integral form, how will it look? Can you tell me? How will it look mathematically? How does expectation look like? Integration fx pi x dx. This is how it would look. Simple. Can I evaluate this integral? No, because pi x is intractable. So I don't know pi x. So if I don't know pi x, I cannot evaluate it. Okay. So what I will do is, let us now bring in the concept of proposal. We don't call it proposal in importance sampling, but it's basically a distribution from which I will sample. And what is the notation of proposal or distribution from which I can sample? Qx. So what I can do is I can divide by Qx, multiply by Qx. I can always do that. So I'll do that. So if I do that, I will get pi x by Qx fx Qx dx. Right? Simple. Now in the expectation form, what is this equal to? If I have to write expectation with respect to q, then what will it look like? This integral. This is also an expectation of pi x by Qx fx with respect to q. So this is equal to expectation, because I cannot sample from pi, but I can sample from q. And to use law of large number, I need samples from. So this is expectation with respect to Q. And what do I have inside? Pi x by Qx Fx. Okay. Now this pi x by Qx, this I will call as weights. This ratio is the weights. So now you see each thing is weighted. When you will write it in the summation form, each xi will have its own weight. So this sorry, this we'll call Wx, which means what I have is expectation with respect to Q Wx Fx, and using law of large number, what will I get? 1 by n summation of Wxi Fxi. So depending on the sample you are drawing, you will get its weight. So now it's weighted. So this is then approximately equal to, from law of large number, 1 by n summation over I W xi f xi. So each xi, each sample you are drawing from Q is now coming with or having its own weight. Clear? What is happening? This is importance sampling. Okay? This is the idea of importance sampling. Simple? Not so simple, because this you cannot use in practice. Okay? Can someone tell me why you cannot use it in practice? When I say practice, I mean, again, Bayesian machine learning. So in our case, we cannot use it, I am saying you. You tell me why. Exactly. To use it, you need pi of x. Pi of x is not known to us. We only know pi star x, right? We cannot use it. So we will talk about how we can modify it and use it. We'll come to that. But before that, let's do some maths. So this is an estimator, right? This last summation I have written is an estimator, right? Estimator of what? Of the expectation with respect to, right? So now how do you know it is a good estimator, a bad estimator? How do you even know? How do we know that this is a good? Yes, so it is used, if pi x is known, it is used in reliability and all those things. So because this, because that's the next question I'm coming to, that how do you know it is a good estimator? And more importantly, what do you even mean by a good estimator, right? So because if it is a good estimator, where good is to be defined, then we can obviously use, and we should use, and we use it. There are many applications of this, okay? But how do you know it is a good estimator? So something is a good estimator if two things are satisfied. One, it has to be an unbiased estimator. Unbiased estimator means that if you take the mean of the estimator, that should give you the original quantity. If you take mean of this right hand side, that should give you E of pi fx. If that gives you, then it's a unbiased estimator. That means it is not biased. If you do it 10 times, take the mean, it will give you the mean. Okay. So first criteria is that it has to be an unbiased estimator. Second, in any sampling algorithm, you also have to report what is the convergence rate, because it is the convergence rate that will tell you how many samples you need, or how does it converge with increase in number of samples. Because I am writing 1 by n, I am saying n tends to infinite. In practice, where will n tend to infinite? It will never. So then what is a good n? Remember the example of estimating pi in practical 0. How many samples do you need? You are doing trial and error. So can we establish something mathematically? So the mathematically, that is known as convergence rate, and that basically we are asking the question how many samples we need, or more specifically, how does it converges with increase in n. How do you define, how do you compute that? Take variance. So whether it is unbiased or not, I mean, you will take standard deviation ultimately, but let's say variance for now. So whether it is unbiased or not is determined by taking mean of the estimator. How is the convergence is determined by taking the standard deviation. Okay, and let us see. Okay, and first we will see the vanilla Monte Carlo, what we discussed last to last lecture, where what do I write? Unbiased means that, what do you mean by bias? Let's see. If I say I am a biased person, what do you mean? That I have some favor, right? I am favoring something and I am not favoring something. If it is biased, then the mean of this, and how do you know whether I am biased or not? You will observe the 10 decisions I have taken, and you will see that in this 10 decisions whether I am preferring someone or not preferring. If I take 10 decisions, 5 times I prefer someone, 5 times I prefer someone, then I am unbiased. In a coin tossing, if I get a probability of 0.5, then that coin is unbiased. It is not biased towards head and tail. Similarly, in this case, it will be unbiased. If you use this estimator, let's say 100 times, you will get 100 estimates. The mean of those 100 estimates should match your mean. So that means mean of your estimator should be equal to the quantity that you are trying to estimate. Then you will call it unbiased. Okay, there are proper mathematical definitions and all those things, but that we don't need. So I'm not going into that. What we need is understanding, and we should be able to connect it with real world problem. So in that sense, okay. And by the way, do not think that we will not use an unbiased estimator. We will use. So when we go into the modification of importance sampling, where pi will be pi star, that will be a biased estimator, and we will be using it. Okay, it's also about, because machine learning, you can see whether a course is applied or fundamental is always relative. Compared to statistics, machine learning is an applied course, right? Although we are doing so much maths, but it's an applied course compared to, let's say, statistics. And since it compared to statistics, it is an applied course, we have to use the best tool that is available to us. If the option is between not solving a problem and using a biased estimator, we will any day use biased estimator and report that this is a biased estimator. That's fine. Or yeah, so it will actually be unbiased in asymptotic sense and all those things. But so those things are there. Those will come later. But we can use biased estimator. And again, as I said, right? So if it is biased, what we will do? We will then say, okay, can it be somehow? Can I somehow show that with some approximation it becomes unbiased? Why am I doing that? Because at the end of it, I have to use it. I have to get results and I have to get it done. That's what engineering is all about, getting things done, right? So that's how it is. Okay. Okay. So as I said, how do we know if an estimator is a good estimator, is a good one? So generally, there are two quantities we can check whether it is an unbiased estimator or not. Unbiased estimator or not. If it is unbiased, we will prefer that. Second, convergence. Okay, what is the convergence rate? Okay, so now remember, in law of large number, we'll start with that only. So in law of large number, we said that mu is approximately equal to 1 by n summation xi. right? This is what we mentioned or studied in law of large number. Now this is again an estimator, the right hand side. I want to check whether it is an unbiased estimator or not. What will I do? I will take mean on the right hand side and check whether that mean is equal to the left hand side or not. So the question is to check if it is unbiased, we take expectation of the RHS. What will I get if I take expectation of the RHS? Expectation of 1 by n summation xi, right? 1 by n is a constant that will come outside. I will get expectation 1 by n expectation of summation xi. Expectation, the operator is additive, it will go inside the summation. I will get 1 by n summation of E of xi. E xi is our IID, E of xi is equal to mu. I will get 1 by n summation of mu. Summation of mu is equal to n of mu. N and n will cancel out, I will end up getting mu, which means without doing anything we know that it is an unbiased estimator. Look, I will show it, but so as I said, we have to calculate expectation of Ixi, which is equal to 1 by n expectation of summation xi, which is equal to 1 by n summation over I expectation of xi. This is nothing but equal to mu. So, you will end up getting n mu by mu, which is equal by n, which is equal to mu. So, it is an unbiased estimator. Okay, as simple as that. In this manner, I am not proving it, you prove it yourself. It is very simple, that what is the whether importance sampling the estimator we got is an unbiased or not. You can very clearly see that it will be an unbiased estimator, because that q and q will cancel out, you will get pi. Okay, so you do it yourself. I will not do it, but you know the process now. Okay, next, convergence rate. Convergence rate. Okay, what is the convergence rate and how do we define convergence rate? By standard deviation. So, let us take variance and then we will do square root of that, that will give us standard deviation. So, variance of the estimator. What is variance of the estimator? Variance of 1 by n summation I xi. What will be it equal to? 1 by n will come outside, or what is variance of Ax? 1 by n square, variance always squares, right? So, 1 by n square variance of summation xi. Can I take the variance inside the summation? Because they are IID independent, so we can, otherwise the covariance terms would come, but they are IID, independence of covariance will be 0, so I can take it inside. So, it will be equal to 1 by n square summation over I variance of xi, this is equal to sigma square. So, what will I get? Sigma square by n, because that will give the summation will give me n sigma square. So, n sigma square by n square, which will give me sigma square by root n, sigma square by n. So, this is equal to n sigma square by n square, which is then equal to sigma square by n. What is the convergence rate? With respect to n, I will say sigma square I will remove 1 by square root of n, which is a very slow convergence rate. Correct. So, at n, what will you want your variance to be? Think about it. You will want your variance of your estimator to be 0, not same. You do not want your estimator to vary. If you take infinite, then this would be equal to 0, right? Because you will want that every time I run, if I run the chain or if I draw enough samples, ultimately it should converge. There should not be any difference, right? There should not be any variance. So if there should not be any variance, so that means at n tends to infinite, this should be equal to 0. And that's what we are always saying, that as n goes to infinite, we get the exact result, right? So here, so convergence basically means that how many samples you need, okay, or how it changes with sample, your estimator. So therefore, convergence rate is 1 by square root of n. This is a very slow convergence, by the way. Why? Because square root of n in the denominator. So that's the point. I would have liked what, 1 by n to the power 10, because that would have given me very fast convergence, but that I will not get. So we have to work with whatever we have. Clear? So now, how is the convergence rate of importance sampling? Because if we can compute the convergence rate of importance sampling, that will actually tell us whether we can improve something, we cannot improve something, or whatever we can do, all of that will become clear from importance sampling only, right? So now, let us focus on, let us study the importance sampling from the lens of convergence, right? Let us now study importance sampling from the lens of convergence, and let's see what comes out. Maybe nothing will come out, who knows, but at least we should try, right? So what is the importance sampling estimator? Importance sampling estimator is, you want to compute expectation with respect to pi fx, and this is approximately equal to 1 by n summation over I wxi fxi, right? W xi fxi. I mean, probably I should write wifi, but that's okay to save space. So this is the estimator, correct? What we want to do, how to compute the convergence? Variance. So we should take variance of the estimator. So for convergence study, so to examine convergence, we take variance of the estimator, right? What is the variance of the estimator? Variance of 1 by n summation over I w sorry xi f xi, right? Clear? Again same thing, 1 by n square, variance will go inside, not only inside, it will go inside the summation. Let us write it down, which is equal to, and let me continue in the next slide, 1 by n square summation over I variance of w xi f xi, yeah, right, which is equal to 1 by n variance of W xi f of xi, right? Why 1 by n? 1 by n will come, n square and n will cancel out, so 1 by n is what will remain, right? Clear? So that means this variance is what I have to evaluate. What is variance equal to in form of expectation? Variance of x is equal to expectation of x square minus expectation x whole square. That is one of the formula. There is another formula, but both are same. So then this in terms of expectation is equal to 1 by n expectation with respect to q. This was also with respect to q, I did not write it by the way. So this is there, square of the quantity inside, square of the quantity that is inside. So basically I am using var of x is equal to E of x square minus Ex whole square. This is the form I am using. So whatever is inside should be squared. That means it will be W square F square. W square x, I am not writing xi, I am removing it because to save basically. Okay. This is 1, and then the second term, okay, f square minus expectation of q wx fx square, right? Clear? So now the first term, what is that equal to? Think of it in your mind in terms of integration and think what is cancelling out. If I write the first term in terms of integration, the expectation integration, what will it look like? What will it will be integration of W square x f square x qx dx. What is W square x? W is pi by q, so W square is pi square by q square. So 1 q will cancel out, right? And then from pi square 1 pi should shift because I want to write the expectation in terms of pi. So you will get, then you will get back W again, pi by q again you will get back. So let us do it, but you should be able to visualize it actually. It's 2-3 small steps. So let us consider the first term. Okay. So expectation over q W square x f square x. Those who are audit may not sign by the way. Okay. Okay. W square x f square x is equal to integration. W square is equal to pi square by q square, right? That's what we defined earlier. W is equal to pi by q. So this is equal to pi square x by q square x f square x qx dx, right? Nothing difficult. Q and q will cancel out. I will take 1 pi on the other side. So this will be then equal to integration 1 pi I am removing, 1 q is 1 pi I am removing, 1 q is remaining. Okay. F square x pi x dx. See, q and q will cancel out, q and q square, 1 q will remain, 1 pi I am taking on the other side, 1 pi I am taking on the other side. So this is what I am getting, right? What is this equal to in terms of expectation? This is equal to, this again becomes W. This is equal to expectation with respect to which distribution? Pi. And what is inside? Wx f square x. Right? What do you think will be the other integration equal to? That's also prove it is unbiased, by the way. Other integration will be equal to u of pi f of x because it's an unbiased estimator. So let us do that also for completeness. So this I will call equation 1. This, the one I just got, is equation 2, and now I am deriving equation 3. So expectation with respect to q, wx fx, this is the estimate, mean of estimator, right? This is the mean of estimator. This is equal to integration wx is equal to pi x by qx, fx qx dx. So you end up getting expectation over pi fx, right? And this also shows it is unbiased estimator, by the way. This automatically shows it is unbiased estimator, right? This is equal to 3. So now substitute 2 and 3 into 1, right? Substitute 2 and 3 in 1. So then what do you get? This is 1, right? This is 2 and 3. So what will I get? 1 by n will remain outside. Then this will become expectation. The first term will become expectation with respect to pi wx f square x. That is equation number 2. And the third term will become square of expectation of pi fx. That is equation number 3. So what we get is 1 by n expectation with respect to pi. You have wx f square x minus expectation with respect to pi square. This means whole square, okay, fx, right? So the convergence rate is still proportional to 1 by root n, but there are quantities inside that are sitting that you can control now, because previously sigma square by n was coming. Sigma square was not in your control. It was sample variance or something like that, right? But now in this, in the numerator, what can we control? What is in our control? Q of x. So you can select a Q of x which can increase the convergence rate, right? You can select, basically you will try to minimize the numerator because you were increasing the denominator. So you should try to minimize the numerator. If the numerator minimizes, the convergence rate increases. So and what do you think it will depend on? Q you can select, so it will depend on also on fx actually. So Q is to be selected by you, but Q is to be selected by you keeping in mind what is the pi and what is the f. Okay. So now one question that often is asked is, what is a good Q? Well, a good Q is a Q that will increase your convergence rate, because this is applicable for almost any Q with very mild conditions. So not only the convergence rate we have calculated, but we can now use it to determine what is a good Q. But remember that good Q is not only a function of pi, but it is also a function of the quantity you are trying to estimate. It is also a function of the quantity you are trying to estimate. Let me try to give you one example very quickly, but let me first write it down. So the convergence rate depends on Qx and Qx should be selected keeping pi x and fx in mind. Okay. So, convergence rate depends on Qx and you should select Qx while keeping pi x and fx in mind. Okay. A very good example of this is rare event probability. Okay. So, suppose I have a distribution like this. Okay. And I am only interested in finding out the area in this portion. Okay. And also assume that this is a mixture of Gaussian from which I can sample. So, I am even giving you a condition where you can sample from this distribution directly. So, let me repeat the conditions. This is the arbitrary distribution but represented as a mixture of Gaussian, and since it is mixture of Gaussian you can sample from it. So, sampling is not an issue, and this will answer the question that you asked earlier, that can we use it in some real application where pi x is known. So, in this case pi x is known, you can sample from pi x. Okay. But your objective is to compute that a small area that you see on the right hand side of the screen. Now, what will happen if you sample from pi x and try to compute that area? Can you imagine what will happen? Because that is a tail region with very low probability. Maybe you have to draw, I don't know, 10 million samples and then 1 or 2 samples you will get there. If you draw some trillion sample, maybe you will get a million sample in that range. And then using those million samples in that range, you can compute the area. Because how can you compute the area if there is no sample you are getting in that area? And definitely will not get sample in that area because of the low probability mass. Make sense? So now can we use importance sampling here? What if I define an importance sampling density which is like this? This is my importance sampling density Qx. I'll tell you that. You say, you ask a good question, you try to answer. Why like this? The question being asked is that why did I choose an importance sampling like this? Because I want to integrate in that area. So I will want sample in that area. I have created a peak in the area where I want to integrate. So now if I will draw sample from which distribution? From this one. Will I get sample in the area I want to integrate? Will I get samples in this area now? In this area, will I now get samples if I draw from this PDF? Obviously you will get, but how many samples? You cannot have a direct delta function. The only way you will only get sample from that if you have a direct delta function. So that's not even a distribution that you can sample from. So what is the question then? What is your doubt? Are you sure about your doubt, or you have doubts regarding your doubt? Okay, and how will you integrate is the first question. So the question is, why are you considering peak in that area? First of all, forget about peak. How will you integrate? How will you integrate is the question. By sampling. Now, if there is what happens in a distribution where there is peak? That is the mode. And what is the definition of mode? So if you draw samples, most of the samples will come from, many of the samples will come from mode region. In Gaussian, most samples comes from the mode area, that's have highest probability mass. So if I create a sample distribution like that, most of my samples will now be in that area. Okay. So as a result, I will now get samples in that area, but obviously I have to integrate with respect to the other one. So I will weight it Qx by pi x by Qx. And with this, with very few samples, I can find it out. Understood? What will I do? So this is what is used for rare event probability. Because this is a rare event, your probability is in the order of, I don't know, 10 to the minus 20 maybe. You cannot even sample, forget about doing anything. The best idea is create an importance sampling density, that is Qx in this case, that is focused in that area, and sample from that distribution and then compute the integral, because with this the convergence rate will increase. So this is one example where I have increased the convergence rate, nothing else, by this selection. Okay. But for our case, this formulation is of no use till now. So let us now come to the actual thing. Okay. And I have 20 minutes, which is more than enough. Okay. So, however, in our case, pi x is only known up to a proportionality constant, right? So basically, we know pi x is equal to pi star x by z pi. Okay, and z pi is not known to us. We only know pi star x. We only know the numerator of our Bayes law. We only know the likelihood and the prior. We do not know the evidence. Now it makes sense. It connects to the problem we want to solve. So we do not know pi x, we only know pi star x. And knowing pi star x, can we use importance sampling? So let us see. So the question is, how to use importance sampling when only pi star x is known, right? How to use importance sampling when only pi star x is known. So let us try to see. What we want to compute does not change. We want to compute with respect to pi only. Sorry, fx I forgot to write. fx pi x dx, right? But pi x is not known to us. So what we know, let us write in that form. Integration of fx pi star x by z pi dx, right? Z pi, is it a function of x, or do you think z pi is a constant? Constant. Normalizing constant is the name, so it has to be constant if in the name there is a constant. So z pi can come outside the integral. So this is equal to 1 by z pi integration of fx pi star x, and now I will do the importance sampling trick, qx dx, right? Clear? What is my new weight now? Pi star x by qx is my weight, not pi by q, and pi star is known to me, so I can work with that. So let's call it w star x, just to separate it out from what we are doing earlier. So then this is equal to 1 by z pi stays outside, expectation with respect to q, w star x fx, right? Clear? But z pi is unknown, so we have to do something about z pi, correct? Let's call it what? Equation 4. So now z pi, What is Z pi? Normalizing constant, but how do you calculate it? Let me give you some clue. Yeah, from here to tell me, how do you compute Z pi? Don't tell that pi x by pi square x or something like that. Don't tell me that, apart from that. Okay, how do you calculate Z pi? What is integration of pi x? 1. Integration of pi star x will be Z pi, right? Property of PDF that it integrate to 1. So if you integrate the right hand side, Z pi being constant will come outside. So integration of pi star x dx would be equal to 1 by Z pi. So integration of pi star x dx would be equal to Z pi. Clear? So Z pi is equal to integration of pi star x dx, since integration of pi x dx is equal to 1. Okay. Now I will do the same trick, pi star x by qx multiplied by qx. Okay. So this is equal to integration of pi star x by qx multiplied by qx dx. This is again my same thing, w star x. What is this quantity equal to then? Expectation with respect to q, w star x, right? This is my equation 5. So therefore, the estimator is importance sampling estimator is expectation with respect to q, w star x fx divided by expectation with respect to q, w star x. Okay. And w star x is known to you, pi star x by qx, pi star is known to you, prior times likelihood. So this can be used for Bayesian linear regression for the problem we have discussed, even without knowing the evidence. The evidence will be handled by the normalizing constants. Okay, by the way, this is known as normalized importance sampling, because the normalized, because you see there is a division there, so that's like normalizing it. So this is known as NIS, normalized importance sampling. Okay. Clear? Now, as I said, this is not a unbiased estimator. This is a biased estimator. Okay. Why is it a biased estimator? Because till now, how are you getting something to be unbiased estimator? We are taking expectation and showing that whatever we want to estimate, we are getting, right? In this case, you can realize there is A by B, and expectation of A is not equal to expectation of A divided by expectation of B. That property is not divisive, it's additive. If expectation of A by B is not equal to expectation of A divided by expectation of B, then naturally you cannot proceed and you will fail. Okay. So we have seen that expectation of pi fx, this is our quantity of that I want to estimate. This is equal to expectation with respect to q, w star x fx divided by expectation of q, w star x. Okay, this is what we just proved, right? And as I said, this is not an unbiased estimator. And that you can, if you want to prove or try to prove it's biased or unbiased, just take expectation and see whether you are able to. So basically, if you take expectation of the right hand side, that should give the left hand side, then it's unbiased. You try taking expectation of the right hand side and see whether you are getting left hand side or not, right? If you are not, then it's biased. If you are getting, then it's unbiased, and you will not get, I am telling you, but you can try. Okay. However, this is unbiased in the asymptotic sense about the mean. So, if you use Taylor series expansion on this thing about the mean, then it becomes unbiased, assuming you are ignoring the higher order terms. Okay. However, this is unbiased in an asymptotic sense. Okay. This is unbiased in an asymptotic sense. So, what we will do is simple. This quantity, let us write it as A by B. Okay. The numerator I am writing A, denominator I am writing B, and that's all. Okay. So, now we will use Taylor series. So, consider g of A comma B as some arbitrary function and expand it about mu A and mu B, where mu A is the mean of A, mu B is the mean of B, using Taylor series. So, can you tell me the Taylor series for g of A comma B? How will it look? G of A comma B. What is the Taylor series for this? What is the Taylor series? Taylor series you should remember. Obviously, it's a multivariate Taylor series, but at least univariate you should remember. What is it? First is you evaluate at the point, which is mu. So, the first thing is you will evaluate G, mu A, mu B. So, that generally we say G naught, right? G naught is what we say, f of x plus delta x is equal to fx plus, what is the second term? G dash. So, G dash in univariate case, we are doing bivariate. So, there will be two G dash, one with respect to A, one with respect to B. So, it will be A minus mu A del G del A, and the second term is evaluated at mu A comma mu B, plus B minus mu B del G del B evaluated at mu A comma mu B plus the higher. Sorry. Oh, acha, okay. Correct. Thank you. Okay. And then the higher order terms, right? Clear? Higher order terms I am not writing, but can write. Higher order terms I am not writing because I will ignore them. So, now take expectation of the left hand side. What will you get? Expectation of g of A comma B. If I take, what is the first term? What will happen to the first term? First term is a constant. Constant of expectation of constant is equal to same. What will happen to the second term? See, del G by del A, that is constant because that's evaluated at mu A comma mu B. So, that's like a constant that will come outside the expectation. Expectation of A is mu A. So, mu A minus mu A, it will give you 0. Third term will also give you 0. Higher order terms I am ignoring. So, I will only have the first term. So, actually now that has happened, expectation of A by B is equal to expectation of A by expectation of B. Because of this thing it is happening, and then you can prove it is unbiased. Okay, so this is, so taking expectation on both sides, you get expectation G A comma B is equal to G at mu A comma mu b. Other terms cancels out, and I have only taken up to first order. Second order terms I am assuming them to be small and ignoring them. And because I am ignoring them, that's why it said that it's unbiased in an asymptotic sense. Because I am saying it is the series is asymptotically going towards 0. So second order term is small, third term is smaller, fourth term is even smaller. So it's like that. Okay. We have not, it came out, but exactly that's what happened, right? Taylor series did that. I did not do that. Taylor series allows me to do that with certain assumptions. Basically, I linearized it. That's all I did. Basically, it's basically linearizing it. There's nothing. You linearize it, takes up to the linear function. Once you become linear function, expectation is linear operator. Is good. No, I will never use it. I said, right? You have two options. One, you do not estimate. Second, you estimate with a biased estimator. For example, suppose even asymptotically, if I cannot prove that it's unbiased, how does it change anything? I will still use it because I have to find out the expectation. I'll just give a disclaimer. Remember that this is a biased estimator. Like if I give you a very large sample, okay, how do you compute the variance? What is the formula for variance? Summation by 1 by n. That's a biased estimator. It should be 1 by n minus n. But you don't care, right? That's a biased estimator. If n is very large, it does not matter, n and n minus 1. But 1 by n is a biased estimator. The unbiased estimator of variance is 1 by n minus 1. So we use biased estimator without even realizing we are using biased estimator. This is the case. So this is a mathematical exercise to show that at least you can prove that it is unbiased in certain case. Okay. But suppose if we even cannot prove that, even then we are fine. We would still use it because it's the only option we have. And it does have its advantages. Clear? Exactly. Other properties like convergence. In this case, convergence, if I'm getting, let's say I have two things. I can be unbiased. I will need 100 trillion samples. And I can be biased and get it done with 1000 samples. I will any day choose 1000 samples because 100 trillion I anyways cannot do, right? So it's horses for the courses, and it's what are the tools available to us, and among them you select the best fit tools. That's the thing. Okay. Anyways, yeah. So now substitute. If I substitute, what? Therefore, if considering g of a comma b is equal to a by b, and using the Taylor series as before, we can show that normalized importance sampling is unbiased in an asymptotic sense. Okay. I'm not proving it, but it's one line proof actually, because I will just put in, I will take expectation of the top and expectation of the bottom. Expectation of expectation will come out to be that left hand side basically. So if I take expectation, okay, since I have what 2 minutes, so I will not write it down, but let us discuss it. Okay. So what will happen if I take expectation of the numerator? What will I get? Expectation with respect to of the numerator. There is already an expectation, that's the estimator. So expectation of the new estimator in the numerator. The estimator is what? You go back, it is there, right? This q we will write in a summation form. So what will the numerator be like? 1 by n summation w star xi fxi, right? And I am taking expectation of that. What will happen? Expectation of f of x with respect to pi you will not get, because w star is having pi star. So you will get integration of fx pi star x dx. Q and q will cancel out, you will end up with get pi star. So that will not be any result. You will get integration of pi star x fx dx. Do it for the denominator. What will you get? Denominator is 1 by, you will get z pi. So that will put inside the integral. You will get the left hand side. So what you will get is, let me show it actually. It was expectation of q w star x fx, right? This is equal to approximately 1 by n summation w star xi f of xi, right? And you are taking expectation of this, so you will take expectation of this quantity. Okay. So this will happen is 1 by n will be outside, summation, expectation will go inside, w star xi f of xi. Okay. So that's a constant, so n mu, n and n will cancel out, so that will be equal to expectation of q wx w star x fx, which is equal to integration of pi star x divided by qx fx qx dx, qx cancels out, you will end up getting integration of pi star x fx dx, right? Do it for the denominator, you will end up getting integration of pi star x dx, yes, and that is z pi. That will go inside and you will end up getting integration of pi x fx dx, which is expectation of pi. Okay. So nothing difficult, mathematical exercise. You will not need this kind of, this kind of question can come in the majors, but for writing codes and all those things, we will probably not need this derivation. Minor, I am going to discuss now. So minor, I am planning to have take the minor next Wednesday during our regular classes, right? Wednesday practical. Wednesday Friday routine. Then I cannot. So then we have, no, not according to the timetable, because it will be on Moodle. So if that is the case, then Tuesday from 7 p.m. Tuesday is 10th, I guess. Minor 12 से शुरू हो रहा है ना? Okay. So my suggestion is that I will obviously finalize through email, but right now I am discussing because many of you are here. So what I am suggesting is, okay, I was not aware of that. Thank you for that. So someday in the evening, before minor. Okay. So 10 I am suggesting because 9 is the deadline for homework. So after that only, it will be hardly 20 minutes exam. You have to bring your laptop on Moodle, not more than that. Major will be, as I discussed, announced in the first lecture itself, pen and paper, and that will be proper to our exam. Yeah, MCQ, fill in the blanks, conceptual questions, and all those things. Okay. So I will circulate a mail to decide the time. Preferably, I want it before the minor. Okay. And it will be what, 20 minutes to 30 minutes, maybe 15 minutes also, not more than that. There will be 10 to 15 questions MCQ, because it has 10 marks weightage, 10% weightage or minor has, right? 15. Yeah, it has a less weightage. Major has more. Major has I think 20 or 25. Minor has 15, right? So yeah, so that much weightage. Whatever I announced in the first lecture, I don't remember. Minor don't have much weightage, so that's why there is no point taking 2-hour exam and giving you these derivations. Okay, so that I will reserve for major. Okay, so that I will reserve for major. For minor, I will circulate an email to finalize the time. The suggested time is Tuesday evening. And evening I'm flexible. You can say 6:30, 7, 7:30. I'm okay with anything. Okay. Second thing, project submission deadline and all those things have been uploaded on Moodle. So have a look. I think it starts from 21st or 23rd, the first report, and it ends. The last report is on November 1st week, November 6th or something like that. Okay. So all those things have been also uploaded. Any questions? Okay. Thank you.